Welcome back, everyone. We're on notes number 15, and I've titled it Slopes of Tangent Lines. That sounds a lot like the title of yesterday's lesson, I guess. So remember the big idea from yesterday. I'll draw the sketch again. So we have some function, whatever it's doing, and we're interested in knowing the rate of change of that function at a particular point. So to get the rate of change, we need to know the slope of the tangent line at that point. But you can't get the slope of a line with only one point. So instead, what we do is we find a second point on the curve. We find the slope of the secant line, which is the line that connects both points. And we use that slope to approximate the slope of the tangent line. And the closer those 2 points are together, the better the approximation for the slope of the tangent line. So today what we're going to do is find out how to use calculus to find the exact answer, as opposed to just fiddling with numbers and getting an answer that's close to what we think it's supposed to be. So remember, the average rate of change is going to be the slope of the secant line. And the instantaneous rate of change is the slope of the tangent line. That's what we're going for. And I'm going to show you one of the methods to do this. Tomorrow we learn a different method, and I'm going to let this point here, the point that we're interested in having the slope of, be the point A, f of A. And then the other point, we'll just call that x, f of x. So if you want the slope of the secant line, all you do is find the change in y coordinates, which would be f of x minus f of a, over the change in x coordinates, which would be x minus a. All right, just a simple slope, y2 minus y1 over x2 minus x1. But if you want the slope of the tangent line, to get the instantaneous rate of change, those 2 points need to be infinitely close together. So this is going to involve a limit. So the slope is going to be the limit as x approaches a. That point that yesterday we called point Q is getting infinitely close to our point P. So it's the limit as x approaches a of f of x minus f of a over x minus a. You take the slope from the average rate of change, but you take the limit of it as x gets infinitely close to a, and that gives you the slope of the tangent line. Now, you may recall when we were evaluating limits algebraically that you had a lot of limits that looked kind of like this. They were quotients, they had some difference on the top and some difference on the bottom, and we had to use algebraic techniques to evaluate them, things like factoring and things like conjugates. The reason you had so many limits like that was to prepare you for this lesson and to prepare you for finding the slopes of tangent lines. So let's do some examples. Find the slope of the tangent line to the given curve at the given point. So here's our curve, f of x equals x squared minus 4x. And we want the slope of the tangent line at x equals 1. So remember, the slope is going to be the limit as x approaches 1, because that's the point we're interested in, of f of x minus f of 1 over x minus 1. That's just our formula that we wrote on the last slide, but I put a 1 in place of a. That's our a. Okay, so we have the limit as x approaches 1 of f of x, that's our function, minus f of 1. Let's figure out what f of 1 is. F of 1 would be 1 squared minus 4 times 1, and that's 1 minus 4, that's negative 3. So we have minus negative 3 over x minus 1. Okay, so that was f of x minus f of 1 over x minus 1. Now our job is to evaluate that limit. So we need to simplify it. We have the limit as x approaches 1 of x squared minus 4x plus 3 over x minus 1. If you try direct substitution, you get 0 over 0. So we need a different method. Let's factor the numerator into x minus 3 times x minus 1, and that's over x minus 1. So you can cancel the factor of x minus 1 from the top and the bottom. Now that you've canceled it, you can substitute the 1 in to evaluate the limit, and you have 1 minus 3, so you get negative 2. So what does that mean? That means that for that curve, which is a parabola, right? Let's picture this. This would be, if I were to factor out an x, this would be the parabola that has a root at 0 and a root at 4 and opens up, something like that. So we're saying at x equals 1, let's suppose that's here, the slope of the tangent line is negative 2. That's what we're saying. Okay, that seems reasonable enough. Now, on to number 2. Find the slope of the tangent line to the given curve at the given point. Okay, new vocabulary term. It's a mouthful every time to say, find the slope of the tangent line, find the slope of the tangent line. So the word for it is derivative. You've probably heard that word before, derivative. Now, the process of finding a derivative is called differentiation. So, the reason this class is called differential calculus is because this class is all about differentiation, which means this class is all about finding derivatives. So, now the cat's out of the bag. Now we know what this class is all about. Finding rates of change. So let's do it. So remember, it's going to be the limit, in this case, as x approaches 2, because that's the point we're interested in, of f of x minus f of 2 over x minus 2. So we're going to have the limit as x approaches 2 of f of x, that's our function, minus f of 2. Let's figure out what f of 2 is. F of 2 would be 1 over 2 minus 1, so that's 1 over 1, that's just 1, over x minus 2. So this should remind you of some of the limits you've done where you had fractions inside the fractions and you had to simplify. If you plug in 2 and do direct substitution, you're going to get 0 over 0. So what I'm going to do is I'm going to multiply the top and the bottom by x minus 1 over x minus 1 to clear the fraction, the little fraction. So we have the limit as x approaches 2, and when we multiply the x minus 1 by the first fraction, the x minus 1 cancels with the 1 on the bottom, leaving us with just a 1, minus, and when we multiply the x minus 1 by the 1, nothing cancels, so we have x minus 1. Notice the parentheses there. If you don't put the parentheses there, you're probably not going to distribute the negative, and then there's going to be a mistake and you're going to get stuck. Don't let that happen to you. Now let's simplify the numerator. 1 minus x plus 1. See, when you distribute that negative, you get plus 1. 1 minus x plus 1 is just minus x. Nope, I did that before too, didn't I? 1 minus x plus 1 is 2 minus x. There we go. I can add 1 and 1. I was adding 1 and 1 and getting 0. Probably because I wasn't showing my work. Bad example. Okay, now remember, when we do these limits and we have 0 over 0, chances are something's going to have to cancel in order for us to be able to evaluate the limit. So do we see anything canceling? Well, actually, 2 minus x is the opposite of x minus 2. So it's like having a positive 5 over a negative 5. You can reduce them to negative 1. So I can reduce this, but it's going to leave a negative 1. Now that we've reduced, let's substitute the 2 in there, and we have negative 1 over 2 minus 1, and that is negative 1. So the derivative of this function at that point is negative 1. What that means is you have this rational function. It has a vertical asymptote at 1. It probably looks like, I'm just guessing, it probably looks like this in some way. And when x equals 2, the slope of the tangent line is negative 1. That's what that's saying. Anything else below there? Nope. Okay, let's go down over to number 3. Find the slope of the tangent line to the given curve at the given point. So find the derivative. Here's our curve, here's our point. It's going to be the limit as x approaches 1, since we're using x equals 1, of f of x minus f of 1 over x minus 1. Let's figure out what f of 1 is. The function is f of x equals square root x. The square root of 1 is 1. Okay, so we have the limit as x approaches 1 of f of x, that's our function, minus f of 1, we just found that that was 1, over x minus 1. Okay, if you plug in 1, you'll get 0 over 0. It's indeterminate. So remember the technique you would use on something like this. If you have a radical involved in a difference, you're going to use the conjugate. So let's multiply by the square root of x plus 1 over the square root of x plus 1. Multiply the numerators together. We know that when we multiply conjugates, the insides and outsides cancel. It gives us x minus 1. And then on the bottom, let's not multiply it out because we notice that we have an x minus 1 on the bottom. That's going to cancel with the x minus 1 on the top. Remember, your numerator is 1. Okay, now let's substitute the x equals 1 in there, and we get 1 over the square root of 1 plus 1 would be 2. So the answer is 1/2. So that is the slope of the tangent line to that curve at that point. If you want to picture it, y equals square root x looks kind of like this, and at x equals 1, we're saying the slope is 1/2. That seems reasonable. Number 4, find the equation of the tangent line. So we have the same equation, the same curve, and the same point, but it says instead of just find the slope, find the equation. So we're looking for a y equals mx plus b kind of thing, and we just figured out that the slope was 1/2. And we know that we have the point 1, 1, so let's just use those to find the equation of the line. If you want, you can use point slope form, or you can substitute 1 in for y, 1/2 in for m, 1 in for x, and solve for b. And then we have y equals 1/2 x plus 1/2. So what we're saying there is that the equation of that tangent line that I drew is y equals 1/2 x plus 1/2. That seems reasonable, that this could be a y-intercept of 1/2 and the slope could be 1/2. Okay, let's see how many more. We have one more. This one is more of an application. If a ball is thrown into the air with a velocity of 20 meters per second, its height in meters after t seconds is given by h of t equals 20t minus 4.9 t squared. Find the velocity when t equals 3. Remember, the velocity is the rate of change of the position, and they're looking for the instantaneous velocity at this particular time, and that means the slope of the tangent line, and that means the derivative. So really important point here, velocity is the derivative of position. Remember that. That is a key point you're going to use all throughout this course. Velocity is the derivative of position. It tells you how fast your position is changing. Okay, so we're going to find the limit as t approaches 3. I'm just going to use t instead of x, of f of t minus f of 3 over t minus 3. Let's find what f of 3 is. F of 3, oops, it's not even f, it's h. Why don't I use h? The limit as t approaches 3 of h of t minus h of 3 over t minus 3. So let's find h of 3. 20 times 3 minus 4.9 times 3 squared. For that, I got 15.9. Okay, so we have the limit as t approaches 3 of our function 20t minus 4.9t squared minus h of 3, which is 15.9, over t minus 3. Okay. Now I'm going to rearrange the terms in the numerator. Negative 4.9 t squared plus 20t minus 15.9. That is not something that I am used to factoring. And if I substitute 3 into the top and the bottom, I get 0 over 0. But I have a hunch. I wonder if you have the same hunch I have. I have a hunch that t minus 3 is a factor of the numerator. Because of all these problems we've been doing, we've been able to factor and reduce and then plug in our number. So here's how I'm going to check it. I'm going to use synthetic division. And this will be a good reminder for you of synthetic division. If you're dividing by t minus 3, you put a positive 3 in the box. And the coefficients of what you're dividing into go in a row. Negative 4.9, 20, negative 15.9. Bring down the first number and multiply it by the number in the box. So it's going to be negative 4.9 times 3, and that's negative 14.7, and it goes in the next spot. And then we add the column. So we add these two numbers and we get 5.3. Now we take 5.3 and we multiply it by the number in the box, and that gives us 15.9, and we write it in the next spot. And then we add the column and we get 0. 0 is the remainder. 5.3 is the constant. Negative 4.9 is the coefficient on the x term. So what that tells us is that we have negative 4.9t plus 5.3. That's our other factor. So we have the limit as t goes to 3 of t minus 3 times negative 4.9t plus 5.3. And that's over t minus 3. So we'll cancel the t minus 3's. And after doing that, we'll substitute the 3 into what we have left. Negative 4.9 times 3 plus 5.3 is negative 9.4. So what that means is that that is the derivative. In other words, that is the velocity when the time is 3 seconds. It's negative usually because it's going down, and the units here were meters per second. Usually the direction is positive is up and negative is down. Okay, so for your assignment today, there's going to be a worksheet with problems similar to the ones we just did in the notes. Thanks, everybody.